Hello everyone. So today I will try to speak English to accommodate our non-Russian speaking audience. I have a bit of a debt from the previous lecture. At the previous lecture I stated the following theorem. Suppose we have Bhargava cubes. Suppose we have two fundamental discriminants d1, d2 less than minus 10 to the 12. Let chi di be the corresponding quadratic characters. The characters that come from the decomposition of the Dedekind zeta function of our field. Let f of s be the following function: zeta of s multiplied by ls chi d1, ls chi d2, ls chi d1, d2. We have discussed that this function is essentially a zeta function of a biquadratic extension generated by square root of d1 and square root of d2. Our goal for the theorem will be to study this function when S is outside the range of absolute convergence of this Dirichlet series. Let also lambda to be L1 chi d1, L1 chi d2, L1 chi d1, d2. Then for sigma between 1 and 0.9, we have the following inequality. F of sigma is greater than 1/2 minus lambda divided by 1 minus sigma multiplied by absolute value of d1, absolute value of d2 to the power 7 multiplied by 1 minus sigma. Okay, so what is the importance of this statement? Well, we want to exclude the case when L function of our character is small when S is equal to 1. So we want to prove that if lambda is very small, then we have a contradiction. And this contradiction will come from this inequality, because from this we see that f of sigma is rather large, because well, lambda is small, so this term will be small compared to a constant. Okay, how do we prove such a result? To prove this result, we need to notice one very important thing. First of all, f of s is a Dirichlet series, right? Bn divided by n to the s, say. What can be said about Bn here? First of all, Bn are all integers, right? Because the coefficients of all the factors are integers. Second of all, B1 is actually equal to 1, right? This is because all 4 series start with 1. And thirdly, we have Bn greater than or equal to 0 for all n. How do we prove such a result? Any ideas, maybe? Yeah, we can show that this is... Yeah, so we've got 2 ideas. First idea is that this is actually a zeta function of a field, and so it is a generating function for the number of ideals, and so coefficients are almost definitionally non-negative. And the second argument is without any knowledge of algebraic number theoretic importance of this function, just look at the Euler product. One way to look at the Euler product is as follows. You see zeta of s is equal to the product of all primes p, 1 minus p to the minus s to the minus 1. And for any character chi, we have a similar product, 1 minus chi of p, p to the minus s to the minus 1, correct? So now we can take, for example, a logarithm of both parts. For example, we get log zeta of s is equal to minus sum over p log, let's write it like this, ln, logarithm of 1 minus p to the s, and then this can be expanded into into Taylor series, and so we have sum over all p and all n, p to the minus ns divided by n. And similarly, logarithm of ls chi is equal to the sum over all p and n, p to the minus ns, chi of p to the n divided by n. Correct? This is due to multiplicativity of character. Now, if you take a logarithm of f of s, you are going to get the following expression. Logarithm of f of s is equal to the sum over all p, p and n, sorry, p to the minus ns divided by n, 1 plus chi d1 of p to the n, plus chi d2 of p to the n, plus chi d1 d2 of p to the n. Now, what can be said about this sum here? You see, chi d1 d2 is equal to the product chi of d1 multiplied by chi of d2. What?
I mean, it's a product.
It is. This thing is also a product. It is equal to 1 plus chi d1 of p to the n multiplied by 1 plus chi d2 of p to the n. And these numbers can be equal to either 0 or 1 or minus 1. So we have a non-negative product here. This implies that the coefficients of f of s, of logarithm of f of s, are all non-negative. On the other hand, f of s is, of course, equal to the exponent of logarithm of f of s, and exponent of the Dirichlet series with non-negative coefficients also has non-negative coefficients, which concludes the proof. Okay, so we noticed that we have non-negative coefficients. What can we derive from this fact? Well, to prove something about properties of f of s outside the domain of absolute convergence. We need to use something about properties of f inside this domain. So let us compute the derivative of f of s at s equals 2. Let's take dm of f over ds to the m of 2. So let's take a derivative and plug s equals 2 inside of it. What do we get? What is the nth derivative of n to the minus s?
It's a logarithm to the power m divided by n minus 2.
What?
Ah,
Sorry?
it's minus logarithm.
So we have sum over n, bn, and then?
Minus logarithm m
Mm-hmm.
power m
To the power m and divided by n squared, right? Okay, now notice that all these summands have the same sign. So minus 1 to the m multiplied by the nth derivative of f at s equals 2 is also non-negative, right? This is the main observation here. What do we do next? Next, let us consider the Taylor expansion of f of s. So f of s is equal to the sum over all m greater than or equal to 0. am 2 minus s to the m, and am is greater than or equal to 0. a1 is greater than or equal to b1 over 1 squared, which is equal to 1. Correct? Notice that AMs are not Taylor coefficients of f, but rather Taylor coefficients multiplied by minus 1 to the m. Okay? Now, what do we do? First of all, it is easy to see that the Taylor series of f of s are not convergent when sigma is between say 0 and 1. This is because our function is not holomorphic but meromorphic instead. So what? Ah, sorry, not a1, a0. a0. So f of s is actually meromorphic. And the only pole of this function is at s equals 1. This is because of the fact that L functions are holomorphic and zeta is meromorphic.
Sorry, why?
The question is resolved, I guess. Define small f of s to be f of s minus lambda divided by s minus 1. This function is, of course, holomorphic, right? So f is holomorphic. We only proved that it is holomorphic when real part of s is greater than 0. But one can actually prove that it is an entire function. But still, let us exploit the fact that f is holomorphic. The expansion f of s is equal to sum over all m greater than or equal to 0, am minus lambda 2 minus s to the m is convergent in, say, in inside the circle, inside the disk, s minus 1 less than or equal to, wait, sorry, s minus 2 is less than or equal to 1.5. Okay? Our function is holomorphic. This means that our Taylor series are convergent. This is where lambda from the theorem comes into play. Okay?
f of s is such ways such sum.
Why is f of s equals to this sum? This is because lambda multiplied by 2 minus s to the m is an infinite geometric series. You can compute that it is equal to 1 over s minus 1. Okay, what do we do next? Well, we have some holomorphic function. Let us estimate the coefficients. Okay.
And actually, we know that it is that the radius is infinite.
Yeah, actually the radius is infinite, but we will not use this result. Okay, so lemma 1 from previous lecture implies the following. When absolute value of s minus 2 is equal to 3 over 2, absolute value of zeta of s is at most 3/2. This you can check, say, using computer or something like this. Okay, or you can prove this as an exercise. Zeta is a concrete function, so you can easily estimate it like numerically. Now, lambda divided by s minus 1, we will estimate this very roughly. This is at most d1 squared, d2 squared. Actually, it is at most product of logarithms, but we will not care about this, okay? Because the most important contribution will come from these three functions. What do we do next? L S chi di is at most absolute value of di, and Ls chi d1 d2 is at most absolute value of d1 d2.
How would you this estimate for lambda?
Lambda is equal to the product of values of our L functions at 1. And we know good upper bounds for this quantity. Notice that we estimate everything on the circle, not inside the disk. Because inside the disk you cannot do something like this, because you have s equals 1 inside it. And also zeta has a pole. Okay, so what can we conclude from this? This means, for example, that f of s is at most what? Well, we get at most 3/2 of d1 squared, d2 squared, right? This comes from zeta and else. And also at most one more d1 squared, d2 squared. Let us estimate this roughly as 3 times d1 squared, d2 squared. Does this work? Everything okay for now?
Can I ask, how do you think zeta is less than 3 quotient?
Okay, this is an exercise. This is an exercise. You can prove this result similarly to the proof of lemma 1 from the previous lecture. Or you can use your computer to plot zeta of s and see that. or you can use Wolfram alpha and plug into it like maximize absolute value zeta of s when and so on. Fine. So what do we get from this? Well, first of all, we get this on the circle, and by maximum principle, we also get the same estimate inside the circle. So we get this when s minus 2 is at most 3/2. This will suffice for our applications. Now, what do we do? Now we estimate these coefficients, am minus lambda. Now, absolute value of am minus lambda is equal to 1 pi. Absolute value of integral over s minus 2 equals 3/2 in absolute value f of s divided by s divided by s minus 2 to the m plus 1 ds. Correct? This is Cauchy formula. Now, what do we get? We get at most 3 d1 squared d2 squared multiplied by 2/3 to the m. Right? Fine. Now, what can we do with this estimate? Take positive integer m. Let us estimate f of s. Not f of s, the series for f of s when m.
Sorry, we know that fm is integer and this.
We know what?
Am is
am is
an integer.
integer, but no. Am is not integer, of course. Am is highly transcendental. Okay? It